Hey everyone! In this video we're going to be taking a look at classifying triangles. So to start off with, I want to take a look at the different ways that we can classify triangles, and then I want to take a look at a couple examples where we have a triangle in the coordinate plane, and we're going to take a look at the ways that we can classify those triangles. So as I said to begin with, here are the different ways that we can classify triangles. There are two main categories. We can classify them by the side lengths, and we can also classify triangles by the angle measures. For the side lengths, we have three options. We have a scalene triangle, which it's a triangle that has no congruent sides, so none of the sides are the same length. An isosceles triangle that has at least two congruent sides, so two of the sides of that triangle are the same. And then an equilateral triangle where all three sides are congruent to each other. For classifying triangles by angles, we have four options. The first one is the acute triangle, where all three angles of the triangle are less than 90 degrees. A right triangle has exactly one right angle. An obtuse triangle has exactly one obtuse angle, so one of the angles in the triangle is greater than 90 degrees. And then the equiangular triangle, where all three angles in that triangle are the same measure. So those are the different ways that we can classify triangles, and we can classify by both of these categories for each triangle. So a triangle we can classify by its sides and its angles. So for example, I could have a scalene acute triangle where all the sides are different, but all the angles are smaller than 90. So now that we have an idea how to classify them, let's take a look at a couple examples where we have a triangle in the coordinate plane. And I want to talk about how we can for sure classify these. So it says graph triangle ABC with A -1, 2, B 6, 3, and C is the point 0, 0. And then let's classify the triangle by its side lengths and its angle measures. So the first thing, let's graph this triangle. So we have A is at -1, 2. We have B is at the point 6, 3, 1, 2, 3, 4, 5, 6, and then up 3. And C is at the point 0, 0. So right at the origin. So this was A. Over here we have the point B, and then at the origin we have point C. And then I will connect these together to form our triangle. Okay, so here's our triangle ABC. Now, I would like to classify this by its side lengths and by its angles. So what we're looking for is we want to know, are any of the sides the same length? And then for the angles, we want to determine if any of them are right angles or if any of them are obtuse angles. So let's start with the side lengths. So it looks like it's not going to be equilateral because AC is definitely a shorter segment compared to AB and BC. But AB and BC, maybe they're the same length, so we should test that out. To figure out how long these two segments are, we have two options. We can use the distance formula, or we can use the Pythagorean theorem. I'm going to use the distance formula. So for AB, the length here, so this was the point -1, 2, and here B was the point 6, 3. So the distance formula, let's subtract our x values. So 6 minus a -1, and that's going to be squared. And then we subtract the y values, so 3 minus 2, that is also squared, and we have the square root of all of this. So if we do a little bit of simplifying, 6 plus 1 is 7, and then 3 minus 2, we have 1 squared. And that's going to be 49 plus 1. So overall, we end up with the square root of 50. Now, I could plug that into my calculator and get a decimal. I could simplify that radical if I wanted to. But really, all I'm concerned with, since I am just going to compare this, I just want to know that it's the square root of 50. So now let's find the length of BC using the same process. So we're going to do the distance formula again. So we have subtracting the x values, 6 minus 0 squared, subtracting the y values, 3 minus 0 squared. It's nice having the origin in there as 0, 0. Makes it easy to work with. So that's going to be 6 squared plus 3 squared, which is going to be 36 plus 9. And adding those together, we end up with the square root of 45. And again, I could simplify that, or I could type that into the calculator, but comparing those two radicals, the square root of 50 and the square root of 45 are not the same. So that means that AB is not the same length as BC, which means that this is not an isosceles triangle. So this is going to end up being scalene. Now the other piece that we want to take a look at are the angle measures. The angle at A, I can tell that this is less than 90, so this is acute. Same thing with the angle at B. It's a very small angle, so that's less than 90. But here at angle C, this looks like it might be a right angle, but we need to be able to justify that. So we can do that by taking a look at the slopes of the two segments. If the slopes are opposite reciprocals, then they're perpendicular, which means we do have that right angle. So let's take a look at the slope of AC. So on the graph, we can just count this. I could also use the slope formula, but just rise over run. So it looks like we go down 2 over 1. So that is a slope of -2. And let's take a look at the slope of BC. So the slope here looks like we go up 1 over 2, up 1 over 2. So that is a slope of 1/2, which means that AC is perpendicular to BC. Since -2 and 1/2 are opposite reciprocals, one's positive, one's negative, and then reciprocal piece, we flip that fraction. That means that these two segments are perpendicular, which is going to give us a right angle at C. So overall, that means that this triangle is scalene because all the sides are different lengths, and it is also a right triangle because we have the one right angle. All right, so those are the methods that we want to use to classify triangles. We can take a look at the side lengths, we can use the slopes to find angle measures if we need to. Let's go through that process one more time on a second triangle. So here we have DEF with the points 0, 0, 3, 4, and -5, 0. So let me start by graphing that. So we have D is at the origin. E is at the point 3, 4, 3, 1, 2, 3, 4. And lastly, we have F is at -5, 0, 1, 2, 3, 4, and 5. So this was D, this was E, and F. And let me connect these together to form our triangle. All right, so here's our triangle DEF. Right away, taking a look at it, I can classify this by the angle measures. I can see that at angle D, we have an obtuse angle. The other two angles are going to be acute. I know that this is obtuse because if this was going to be a 90-degree angle, the segment DE would be going along the y-axis. But since it's rotated past that, that means that the angle is greater than 90. So angle D is an obtuse angle. So overall, the triangle is obtuse. Taking a look at the side lengths, it looks like we have two segments that may be the same length. So we're going to want to test those out. Segment DF, this is just a horizontal segment, so we can count how long this is. So from F to D, this is 1, 2, 3, 4, and this is 5 units long. For DE, we are going to have to use the Pythagorean theorem or the distance formula. Why don't we use the Pythagorean theorem this time? So I can draw in a little right triangle. So we'll just drop this down, and then we'll go over to D like this. So that's a little right triangle here. And then we just want to find the length of that hypotenuse. So the bottom of my right triangle is 3 units. My vertical segment here is 1, 2, 3, 4 units long. So then to find the length of DE, we can use the Pythagorean theorem. 3 squared plus 4 squared is equal to my hypotenuse squared. So that's going to be 9 plus 16 is equal to x squared. So that's 25 is equal to x squared, and taking the square root of both sides, we end up with the hypotenuse DE is 5 units, which is great. So that means that DF is equal to DE. So these two segments are the same, which means that this is at least an isosceles triangle. The segment EF is clearly longer than either of those, so this is not an equilateral triangle, it's just isosceles. So we have the one obtuse angle, we have the two segments are the same, so this is an isosceles obtuse triangle. So there we go. Again, the methods that we're using here, we can use the distance formula or the Pythagorean theorem to find the length of segments and then compare them to each other. We can use the slopes of our sides to take a look at how big our angles are, and the combination of all that allows us to classify these triangles in the coordinate plane.